Hello folks, my name is Romina, and today I'll be presenting our project on interactive theorem provers for proof education, advised by Manoel, Ribeiro, and Milano. And before I jump into the topic itself, I'm kind of curious, have folks here worked with interactive theorem provers before, for the most part? Okay, a large majority, perfect. And for those who haven't, I'll also give an overview of what they are, so no problems there. Okay, but just before we jump into it, so a few observations that I'm sure folks are familiar with as well. But as we know, proof techniques play a key role in the undergraduate and graduate CS curriculum in a wide range of courses, so all algorithm courses as well as formal methods, PL and whatnot. And the observation that we have at hand is that CS students tend to, one, struggle with proof-based content and also show low engagement and also interest in the material as well. So in response to these observations, there have been a lot of investigations, so especially searches for proof technologies. These kind of range from LLMs to like intelligent tutoring systems and also different approaches. But essentially, the search for these proof-based technologies so that they can support students with learning and also increase engagement with the content as well. And specifically, there's been a lot of interest recently in using interactive theorem provers, or ITPs, as these candidate learning tools in educational contexts. And for our specific scenario, we were interested in seeing whether how well ITPs support the range of proof techniques that are covered in the CS curriculum, and how they might be improved to do so as well. But just before we jump into that, in terms of the work that we set out to do with our project, we had three different components. So the first was a user study so that we could collect students' perceptions of ITPs in an educational setting. So the goal of this component was to really validate the educational promise of ITPs and add an existing data point to the existing, literature on the ITPs use in education. And then we set out to do a case study, and here the goal was to prove 5 distinct proof exercises with 2 ITPs. So we used Lean and Rock, and the goal here was to compare the proof development process against the pen and paper process. And as a part of that, we also did a heuristic evaluation using Jacob Nielsen's usability heuristics, which is very well known to the HCI community. And the goal here was to evaluate the proof development process with these 2 ITPs and really try to identify the educational strength and limitations of ITPs and see what can be done to make them into better educational tools. So with that said, just a quick overview of interactive theorem provers for those who might not be as familiar with them. So essentially, you can think of them as an IDE for proof development, the idea being that as the user, you essentially use the proof commands that are known to the ITP. And what happens is that the current proof state gets sent to the underlying logic system, and based on whatever tactic or command you've applied, you get an updated proof state that gets sent back to the user, and it essentially displays a series of feedback and sub-goals that essentially the user has to tackle in order for the proof to be complete. And just to see a concrete example of that, so this is an example with a lean ITP. You can kind of see in our claim over here, so you can see the variables that you have available to you, the hypothesis that's available, and the conclusion that you want to kind of make. So that's all part of your claim. And then you essentially take these, you use the proof commands known as tactics. So you apply those as the user. And essentially, as you do that, on the left side, you can kind of see the proof state, and it essentially keeps track of all the things that you have available to you. And here it kind of shows the goal. So if you go to the next step, you can kind of see how, based on the tactic that you've applied, it'll update the proof state for you. So it's essentially like gamifying that proof development process. And for most common ITPs, at least in the context of Lean and Rock, this is what the development process looks like. So with that said, in terms of like the current literature, so there has been a lot of studies advocating for the use of ITPs in this educational setting. Oftentimes, a lot of the arguments have to do with the fact that ITPs can act as active learning tools because they give this automated feedback at every step of the proof development process. And they can also, like sometimes the arguments kind of talk about the apprenticeship model of learning, where the idea is that the expert shows the student how something is supposed to be done. So that's often done in the classroom setting. And the second part is essentially, as the student, you have to essentially exhibit a similar process for another task, and you have the expert give feedback. And I think oftentimes in an authentic classroom setting, we don't really have a lot of resources for that second step. And folks think that ITPs can essentially help fill that gap since the ITPs do give feedback at every step. With that said, there have also been some studies trying to integrate ITPs into educational settings, and there have been both pros and cons as a part of these studies that have come up. So oftentimes students tend to really like the immediate feedback that are given by the ITPs, so those are found very useful. But there are some issues as well, so specifically syntax of ITPs, generating a steep learning curve for students. So that's oftentimes called out in the literature. And I think specifically for us, we were interested in seeing how these issues arise in the context of different proof techniques and what can be done within that area. So with that said, I'm going to quickly jump into our user study and just walk over what we found from there. So the goal here was to really get an understanding of existing perceptions and see how ITPs do in their current state in an actual authentic classroom setting. So what we did here, we essentially had students on a hands-on introductory formal methods course, and as part of this course, it was essentially 6 of the lectures introduced students to the ROC ITP. So we had students, as a part of those lectures, complete a series of our reproved surveys. As a part of our surveys, we had a mix of Likert scale questions where they essentially talked about their experience, where they ranked their experience with the ITP. And we also had a mix of open-ended questions as well. And as a part of the open-ended questions, we did a thematic analysis to see what issues arised and what students liked about working with ROC as a part of the course. So in terms of the surveys, so we had initial surveys, which was administered before the first lecture to assess students' comfort with proof techniques and any prior experience that they had. We then had an experience survey, so this was administered at the end of each lecture to gather feedback on students' experiences with ROC during the in-class exercises. And then we also had our exit survey, which was given at after the very last lecture to collect reflections on the participants' overall experience. So with that said, just in terms of the student background, so we had 17 students in the course, and they were all invited to do the surveys, and 8 of them participated. So none of these students had worked with ITPs in the past, and most of them, 62.5%, felt uncomfortable with formal proof methods. So these weren't really students who you'd call experts in the setting of like formal proofs or proofs in general. And in terms of their experience, so the first finding was that ROC can actually be useful in educational settings based on the data that we got. So we actually found that 75% of students reported a positive experience with ROC, 50% found the proofs to be easier than pen and paper proofs, and 62.5% expressed interest in using this in the future, and 75% would even recommend it to their peers. So we had a lot of positive stats on it, and we were also curious to see what exactly were some of the features that students enjoyed. So we did that through our thematic analysis. So visualization features got called out a lot. This oftentimes refers to the proof state that students would see on the side. So students quite liked seeing everything worked out on their screen and seeing the current step visualized and essentially having it confirm the correctness of the whole proof. So that was one of the positives that led to those stats. We also had the feedback features, so students calling out that it was very clear when they were stuck in a proof, since at every step you do get feedback from the ITP, and they also liked how they could immediately know when something was wrong, which is not often the case when you do a pen and paper proof. And they also quite liked the systematic approach, so essentially breaking down this idea of proof development into this step-by-step process where you have to essentially think of each step independently and then try to proceed from there. But similar to the literature as well, there were some usability issues that arose in as a part of our user study as well. So specifically, 50% of students found the interface and commands difficult to learn, and when we tried to understand the root sources of those, so some issues that came up, the complex syntax was definitely one of them, with students finding it hard to use the correct syntax and thinking that they need to essentially memorize the syntax. Proof translation was another aspect, so a lot of students thinking that, okay, if they figure out the proof on paper, they couldn't quite translate it to the ROC proof right away, so there were some unable to make the parallelization there. And another issue was just the confusing error messages. So sometimes with the error messages not really pointing out what the issue at hand is, and students not really knowing how to proceed forward. So with that in mind, we essentially, through our user study, got an idea of like, okay, similar to the existing literature, there are positives and there are negatives. And through our case study, we were really interested in seeing it in the context of different proof strategies and seeing how those issues present themselves. So that said, as a part of our case study, we essentially proved 5 different proof exercises with both ROC and Lean. You can kind of see the different proof exercises that we tackled right on the screen over here, and just an example exercise at the bottom. So these exercises were from a discrete math course that was a part of an undergraduate CS curriculum. So these are the types of exercises that you'd expect your CS undergraduate student to be able to do. We were interested in seeing how that essential process would look like if you were to do it with an ITP. And before I kind of jump into one example of one of those exercises, just so that we can see what the proof problem, what the formalized proof looks like versus a pen and paper proof, I think our big takeaway here was that both ROC and Lean can support the formalization of our 5 exercises, but that Lean supports the line-by-line forward reasoning slightly better than ROC does, because ROC requires a more tactic-oriented approach. And as a part of that, Lean more closely resembles a pen and paper proof. And I'll just showcase that in a little bit with one of our exercises as well. But as a part of our case study, this is one of our main takeaways there. With that said, I'm going to now jump into one of our proof exercises. So this was the direct proof for first order logic. And here we were trying to prove that for every integer a, if 5a plus 11 is odd, then 9a plus 3 is odd as well. And this is an undergraduate student's pen and paper proof. So you can kind of see how as a part of it, you essentially just start from the hypothesis, you break it down into what it means to be odd. And it's just a bit of arithmetic and manipulation in order to show that 9a plus 3 can also be expressed in the odd format as well. And you just call out what that factor is as a part of it. So this is the pen and paper proof that a student was essentially right. And if we try to do a similar thing with Lean, so this is a Lean proof, you can kind of see a lot of similarities in the sense. So again, you have your hypothesis over here and what you're trying to prove. And at the very start, you essentially you try to pull out the fact that 5a plus 11 can be written as odd using the obtain tactic. So that introduces the k factor for you right there. And then from then on, a slight difference is that at the very start, you do have to call out what the factor that you will use to prove 9a plus 3 is odd. So you have to call off that right off the bat, whereas in a pen and paper proof, that's more of a discovery process for a student. But once you have that through Lean's calc block, you can actually do that very direct arithmetic that you would do on a pen and paper proof and capture that right here as well. So there's some nice parallel to what you would do as a student on pen and paper. But now if we jump into the ROC version of it, it's slightly different because we don't have a correspondent to a calc block here. So in terms of how you would go about the proof here, so you'd first have to just introduce the hypothesis that you have at hand. And once you've gone from there, you will do a similar thing with trying to show that 5a plus 11 is indeed odd. So you introduce the k factor there. But because we don't have this calc block that supports forward reasoning, you essentially have to take each of the arithmetic steps that we had as a part of the pen and paper proof and then make them into separate assertions. So that, in some sense, doesn't really parallel what you would do on a pen and paper proof. And as a student, this oftentimes does catch students because you have to prove each step separately, which for longer proofs can be a lot more complicated for a student. And then you would apply a rewrite multiple times, essentially, to then bring it to the conclusion. So in terms of ROC, there are some differences in terms of how you would go about with the pen and paper proof, whereas with Lean, it better supported that in our context for our exercises. And although I'm just showing this for exercise 2, this was a pattern that kind of emerged across all the different exercises that we were covering through our case study. Okay. So that said, the big takeaway from the case study was that obviously both ITPs are able to cover the range that we had selected for our proof exercises, with Lean better supporting the forward reasoning, so better paralleling pen and paper proofs. And then we had the heuristic evaluation part of things where we try to essentially understand the strengths and limitations and see what can be done with some of the limitations that arose when working with ITPs for these proof exercises. So with that said, I'll quickly just show the Jacob-Nielsen's usability heuristics. So these are heuristics that are very often used by the HCI community when trying to evaluate new systems for different target audiences. So you can kind of see the range of heuristics that we have here. So visibility of system status, match between system and world, user control and freedom. So very varied range of them that are often used when you're trying to evaluate a system. And specifically for today's presentation, I'll focus on these 3 heuristics, so match between system and world, recognition rather than recall, and help users recover from errors, because those were the ones that we had the most interesting results for. But we do have more detailed overview in our paper about the other heuristics as well. With that said, I'm going to quickly jump into the second heuristic. So this was match between system and real world. So obviously, as we mentioned before, with Lean, so one thing to note is that it has default infix notation, which better parallels what you would see on pen and paper. It also has the support for math symbols, so for all there exists. So again, better paralleling what you would do on pen and paper. It also has this forward reasoning and computation support, which again makes things seem more similar to what a student would do on pen and paper. Now, if we were to look at rock, it does have this default prefix notation, which for students who are directly coming from like a math background, let's say, that might not hit as quickly. It also has less support for reasoning and computation, so you have to essentially break each step down into its own assertion. So again, causing a little bit of mismatch between the pen and paper proof and the formalized proof. And this also kind of relates to the user study theme that we had about proof translation, where students thought that there wasn't really a direct match with what they were doing on paper, what they were thinking through when they tried to make the proof work on their ITP. So that was with the match between system and real world. So for the 6 heuristics, so this was recognition rather than recall. So something to note is that both of these ITPs do provide search support. So once you know what tactic you want to work with, you can essentially they provide search functions that help you look through the documentation of those specific tactics. But as a user, you essentially need to remember the proper application of a tactic and how you're supposed to use it. And this relates to our user study theme of complex syntax. So it's students thinking they have to memorize things essentially to be able to work with these ITPs. And that was something that came up as we were working through our case study and doing the heuristic evaluation as well. And I think on our end, we thought that maybe providing more concrete examples of tactic applications will better support example-driven learning. So you can kind of imagine this almost as a hover over feature, where as a part of hovering over the particular tactic, the student can see examples, and then they can try to essentially mimic that into the particular scenario that they're dealing with. So then for the ninth heuristic that we're going to talk about today, so this was help users recover from errors. So oftentimes the errors from these ITPs, and this was something that we noticed in our case study as well, they tend to be too technical and not very actionable. And oftentimes they tend to be very low level as well and not really directly hitting what the target issue is at hand. So for this particular example here, so you can see an error message from Lean, and you can kind of see the corresponding proof that we have here as well. And the issue at hand, you see the red squiggle, and the real issue at hand is just that we have this invalid token, the hyphen. That's the only issue that we have. But the error message itself kind of talks about the rewrite tactic not being able to progress. So oftentimes the error messages don't really point you in the correct direction, and that can be very frustrating to students who are mostly using these tools for a proof development process rather than learning to work with the tool itself. And this was something that we noticed with Rock as well. So this wasn't just a Lean issue, but definitely came up with both ITPs. Okay, with that said, some of the big takeaways that we had. So obviously, ITPs do hold considerable promise as tools for proof development. Some themes that came up, so they can facilitate the learning of formalization, and they in some sense gamify the proof development process, which can be a bit more fun for students to kind of go through. And they also provide that instant assistance that oftentimes is very hard for us to provide in a real classroom setting just because of the limited resources that we have at hand. But at the same time, their usability will need to improve before we can really repurpose these tools as candidate learning tools for a larger population. Specifically, so in terms of future work, there can be a lot done to essentially make these tools into better educational tools. And some of those we kind of directly called out as a part of the heuristic evaluation. So one, trying to improve the error messages to be more actionable and personalized. Two, trying to strengthen the support for example-driven learning. So essentially trying to make the tactics a little bit easier to work with. And also three, to further help with the learning curve, we thought it would be very interesting to look into automated assistance, so perhaps through LLM integration or AI integration of some sort. Other things to also keep in mind in terms of future work, obviously there's a lot of limitations as a part of our work since it was limited in scope, but exploring perceptions ITPs with a broader population, we were kind of restricting the size of our sample there. Also exploring a broader range of ITPs, so in our work we specifically focused on two, so Lean and Rock, and there's a much wider range to look at there. And we were also very interested in exploring ITP formalization of a broader range of proof techniques, because we were kind of restricted to 5 techniques in our work. And I know there's been a lot of work in UK actually in terms of trying to formalize the mathematics undergraduate curriculum. And we thought it would be pretty interesting to try and parallel that work and do a similar thing for the CS curriculum as well. So to try to cover the broad range and see what issues arise as a part of using ITPs for that process. But with that said, thank you for listening. So that is the end, and I'd be happy to answer any questions. but I don't think the mic is working.
Oh, there it goes. All right. Thank you for the talk. It's very interesting. I was wondering if you had any observations or noticed anything about students over-relying on an ITP. So for example, the ITP will put goals in front of them and tell them what the next step that they need to prove is. Did you notice any students that hurting their ability to write a pen and paper proof where they maybe over-rely on the ITP putting that next step in front of them?
So not in particular in our context, because for the course that we were working with actually, so the 6 lectures that used rock were actually at the end of the course. So up to that point, students were actually doing everything on pen and paper. So the scenario that we ran into a lot in our case was that students would actually try to logically think through it on pen and paper first before trying to translate it to rock. So we didn't run into that issue as much, but it'd be interesting to see if that would potentially arise if we had flipped the ordering of the course material.
Yeah. Thanks.
Yeah.
Great talk. It's really nice to see someone taking the annoyingly hard task of trying to justify kind of something that I think the field intuitively really wants to have happen, and a number of us have tried to do in various capacities. Rob's question kind of got to my first thing about transfer in some sense, right? Because I think what I've noticed in my own classroom is the transfer problem from ITPs to paper proofs a really real phenomenon, and something you can't kind of overestimate. I'm kind of curious if you saw another phenomenon in your class, in your data gathering that we saw at Penn in our graduate class. I think a lot of people see in their graduate classes kind of the phenomenon of the bimodal split with ITPs, where basically the functional programming nerds get it and then everyone else hates it. And yeah, I find that has been, overcoming that's been very difficult for classroom deployment. So.
Yeah, so that's a very interesting question, because I think before looking at the data, we were also kind of expecting a similar trend. But interestingly enough, because all the students that at least participated in our survey, none of them were really comfortable with formal methods, and majority of them had not worked with ITPs in the past. So out of that population, we still got a lot of positive signals in terms of using these ITPs for that educational context of things. But I think going into it as well, we were kind of expecting a similar pattern of people who weren't really as into formal methods or these tools to begin with wouldn't really enjoy them. But from our data, at least, again, limited in scope, but we didn't really get that hypothesis to go. Yeah.
Just dawned on me real quick, in your deployment of it, did you, in your introduction to ITPs, did you use as a test bed for introducing functional programming? Because I think that actually might be a distinction in curriculum. So if you avoid that, then maybe you avoid that stigma from arising.
Yeah, so I think in our context with the course itself, it was basically targeted as a formal methods course. So we were covering a majority of topics from lambda calculus to core logic. So it wasn't really framed as a formal, a functional programming course, if that makes any sense. More so as more of a formal methods course. So maybe that could potentially explain some of those trends.
Functional programming sucks.
In a similar way, you need to plan out and design what your program is going to be before you make it. I imagine you need to do the same with the proof. Have you put any effort towards how you would systematically develop a proof in an ITP?
So I think as a part of our, at least when we were doing the case study, I think that oftentimes the approach that we took was to try and take the pen and paper proof and try to translate that. So I think for us it was a matter of going from the pen and paper proof, trying to formalize that. So we didn't try to formalize the approach that we took. So I think as a part of our work, we didn't try to make a framework of what that approach looks like. But I think as a part of the experience itself, oftentimes our approach was to just take the pen and paper approach and try to see what the corresponding formalized way would look.
Last question now, but maybe the next speaker could already start setting up so that we are.
Great talk. I'm sort of coming from an education background, and I don't have too much PL or math, formally. But I know there was some discussion about a previous talk went over an educational a subset of pirate. Mm-hmm. Have you thought about if that would be like a good solution maybe to some of the experiences that you were seeing with students, their issues. Like, is there a subset of this rock or lean that you think would be a good, like, minimal set of features that would be good educational in this setting?
Yeah, I think definitely like there's a lot of, I guess like if you were to like separate some of the features, I think if we were to like integrate those into like more educational based tools, that definitely is one way to go about it. I think right now the approach that a lot of folks are focusing on is in terms of like repurposing the existing tools as things that can be used in an educational context. But I think it'd be very interesting to try and take it from the separate approach of like, okay, these are the features of these tools that work great in an educational context. So let's take them into like another educational tool and see how that goes. So definitely as part of future work, that'd be very interesting to look into.
Yeah, thank you very much. Thank you.